Okay, let's go through this. Let's go through this with the remaining time. The first section of this review notebook is pretty straightforward, I think. More or less stuff that we've both covered in previous classes, as well as this lecture. So I guess what's different, or what's in the first part, we're looking at we're loading the iris data set, and right off the bat we're really throwing away the labeled data and we're fitting it to the we're just applying k-means to sort of apply our fit. We want to see how k-means sees the different labels of the data. We know a priori that there's 3 labels to the data. Because there's 3 different species in the data set. So k-means, when you set k equals to 3, it's pretty similar to what the actual values are. So it's interesting that k-means gives similar results to, in the iris data set, there's a pretty good separation, or at least there's not a lot of overlap between the two different species, even though they sort of group together as one group. There's not too much overlap between these two groups. So k-means models iris pretty well. When we break it down, we see that a little bit better. One point I want to make about k-means that I didn't mention is making sure that your scales for your axes are consistent. We talked about that on k and n, where it's really important for distance-based, whenever we're applying certain distance-based metrics, we want to make sure that we're sort of looking at things on the same scale. So one thing I'll put on k-means is an important pre-step is to equalize distances first. And we can do that with standard scalar. There's the standard scalar module in scikit-learn. So in other words, if we have say sort of 2 clusters that are highly skewed in one dimension, we'll get better results if let's call this x1, x2. When we equalize these, we'll get something that's a little bit more amenable to k-means. Scikit-learn does this already with when you call fit on the data, it will automatically do this, but it's an important detail. It's very important that this is a very critical step in k-means. That's why I mention it here. Another new feature that we're sort of looking at here is plotting in 3D. So when you visualize this in 3D, again, it's consistent with everything we've looked so far. No surprises. We can see that the clear separation exists not only across 2 independent dimensions, but when you plot all the dimensions together, you see a clear separation boundary between really the 2 clusters that are present in this data, and that's reflected in the parallel plot as we went over. So looking really the visualization. Can I? Is there anyone's charger? Does anyone have a Retina charger I can borrow for? Nice. So the most telling plot, the most telling analysis that we've, this whole analysis is really this silhouette plot, looking at the silhouette scores, and it agrees with our reason, agrees with our observations, because what this silhouette plot is telling us, we have 3 labels. We have 3 labels, but the clustering is stronger for 2 labels than it is for 3. And that just means that two of the species we have are more similar than they are different. Yeah, and I guess the silhouette score, I guess the more and more we cluster, the weaker the silhouette score, the silhouette coefficient gets. This doesn't always happen. Sometimes you'll have a silhouette score that will be really, really noisy. In general, like when choosing number of features or how many degrees our polynomial has, we want to keep things as simple as possible, all else equal. So, try to keep k small. If it makes sense, all else equal, choose the smaller version, the smaller value of k. Sort of Occam's razor. Again, when we look at the sum of squares, when we look at really like the cost function, really what we call inertia, the inertia score that sklearn uses, we see a significant drop. Well, I guess let's start at 2 because it doesn't really make sense for any value less than 2. I'll blow this up a little bit to make it easier to see. So sometimes you see another method being used called the elbow method. In other words, seeing where you see a significant drop in your cost function. Let's do 16 by 16. Right, so we have, if we look at the cost function, and by cost function I mean the weighted sum of squares, the inertia, there's a big drop from 2 to 3, and there's also a meaningful drop from 3 to 4. And this is monotonically decreasing with increasing k, because as you can imagine, every time we add a cluster, the total sum of squares to the centroid, we have more centroids, so the total sum of squares is going to be different. But sort of where you see the sharpest change, where you sort of see the greatest difference in the slope is from 2 to 3 and from 3 to 4. This is sometimes called the elbow method for seeing where you see the largest value of k. I don't prefer the elbow method because it's just sort of objective. It's sort of like, astrology, where you're trying to like find which values, which angles are most strongly changing, or really where the elbow is. With the silhouette coefficient, it's very, very clear. Whichever value is higher on the y-axis is a stronger clustering. The Beer exercise is also similar. I'm not going to go through it because I think that the third part of this in class, which I don't think you guys have had the chance to get to yet, is much more interesting. So I mentioned Google and Google, what Google does and what search engines do, and a major aspect of data science, machine learning is looking for where there are relationships that exist that may not be obvious at a high level. This exercise is worth doing on your own. I'm going to go through it right now and I guess give you sort of the high level solution. And again, this is an optional exercise, but it's really interesting, and you can have a lot of fun with it, and you can get pretty far and do some stuff without having to do too much work. So really, some of the tools we're using here are new. So BS4 is a Python tool called Beautiful Soup, which is really an HTML parser. It's an HTML and text parser, so it can extract information from HTML. Remember, we actually did use it previously in our scraping in the lab when we talked about scraping. Requests is just really what you would call an API client. It just interfaces with the web and just can make API calls. So using Beautiful Soup with requests basically allows us to fetch data from the internet that doesn't necessarily conform to a data frame format. So I define a URL here, and again, there's nothing special about this URL. There's 2 parameters that are going on. I'm doing a Google search. So google.com/search, anything you see past the question mark in a URL are parameters that are passed to the search. So the search query is Python, and I'm basically getting 500 results, right? So if I were to cut and paste this, unsurprisingly, I would get a result with just basically a giant page of results. I could go more, I could go less. but I just sort of chose 500 because so it wouldn't take I didn't want it to take too much time to run. This URL, this percent sign, this is called string interpolation. So URL is a string, and this percent sign is basically replacing this percent %s with a 0. So it's just effectively saying the same thing as 0. So I get the data. Huh? Oh yeah, I'm sorry. Oh, it's too big. So I call request.get. It's just sending a get request to that URL, and I'm parsing it with beautiful soup. And I'm just basically I'm just extracting the text, right? So I'm just looking at the description. Every URL that you get back from Google has that nice little description below the title. And again, I'm just keeping this as simple as possible because it's always better to make things as simple as possible. So there's nothing, there's a lot of stuff going on behind the beautiful soup, behind the scenes, et cetera, et cetera. But the data frame that we get back, again, just has all of the descriptions of the search results. So official site for the interpreted interactive. This is basically the Python language. Python is a widely used general purpose high-level programming language, et cetera, et cetera, et cetera. As we look at the top results are really, surprisingly or unsurprisingly, so the Python programming language. But then as we sort of scroll down, there are some that are obviously not Python. The aliens are voiced by Monty Python members, some Monty Python mumbo jumbo. So how do we find, some of these are clearly related, right? So of these first 10, 9 out of 10 are related. One of them, the aliens, et cetera, are not. And you can imagine that we've talked about features, extracting features from images, extracting features from general data frames. So how do we look at this from text? And so to sort of recap, previously when we did Naive Bayes, we used both count vectorizer and TF-IDF vectorizer. So just to sort of recap, TF-IDF vectorizer count vectorizer will take the counts, it'll take each word that I have, and it will basically give me, each word becomes its own feature, and the number of words that occur are basically the values of that feature per document. TF-IDF is similar, but it sort of applies an extra step where it applies a greater value for rare words, and it applies a less, it penalizes common words. So one of the problem with count vectorizer is that you don't want to count or sort of bias towards frequent or common words. You want to look for words that are more telling, like Monty or SQL alchemy, or things that are more rare. And so TF-IDF vectorizer will take that into account. And by the way, Google does use either TF-IDF or something very, very similar to in its scoring algorithm for how it looks at really keyword value. So TF-IDF vectorizer comes up a lot in keyword search, and this is a very concrete example of that. So just like with anything else in scikit-learn, I build my TF-IDF vectorizer, and 2 steps, I get the feature names, and I transform, and I get a very, very sparse matrix, right? So I get sort of, some words are very, very uncommon. If I scroll to the right, I'm using an n-gram value of 2 here. In other words, it not just counts words, but it counts sequences of words up to 2. So again, it's what we would call a sparse matrix. In other words, it's almost all 0. And I'm going to apply k-means clustering, the same exact, in fact, I cut and pasted this code. This code is almost exactly the same as what I plotted up here to plot the k-means, the clustering, the silhouette score on these, I guess for these flowers. I'll make the figure size larger. Just cut and paste this. And I'll make the figure size larger down here as well. I already did that. Okay, never mind. Okay, so again, same process. I'm fitting k-means for each k up from 1 to 35. I don't really need to go much higher than 35 because I'm just sort of modeling noise at that point. And then, again, same thing. You can take the sklearn metrics already define that. So we plot each value of k, and what do we get? I guess it'll take a little longer. There's a larger data set than the iris data set. And so, sort of interesting. We got the highest value for 2, 3, and 4. And I guess it's sort of interesting, right? So you can imagine there's sort of three terms that are sort of like most salient. There's MontyPython, there's documents that are, I guess, Python language. There's documents that are Python the snake, and there are documents that are, I guess, towards MontyPython. And I guess we're sort of seeing clusters in those domains. The clustering here isn't strong. When I did this, there may be a mistake. I may have introduced a mistake when I just ran it now. When I ran this at home, I was getting 2 and 3 were stronger, and it decreased pretty rapidly after that. So I may have introduced a bug. Anyhow, you guys should reproduce this, and you guys should explore this, because it's interesting. And there's you know, this is a small data set. It's sort of difficult to say if how meaningful it is, but you know, you can imagine that services like Google, etc., Bing will use these sorts of analyses, sorts of clustering analyses, to see documents that are related, and then you know, even some of the scoring algorithms on how they rank documents are based on these methods as well. So I just wanted to give you sort of a more interesting and I guess more unorthodox application of k-means, you know, and how it might work with document recognition. And yeah, I'm pretty sure that 2 and 3 are supposed to be higher, but in any case, it's something that's definitely worth exploring on your own. Cool. So, any last questions? I do want to mention, or at least point out, that your project 2 part, I guess part 2 of your project is due. I think next Tuesday was 14th, Tuesday, Thursday. 5/14 is when you're. I believe it's Tuesday. So really, that's the second phase. The second phase is really the modeling, the machine learning part of your project. It's probably going to be the most difficult, but I just want to point that out as well, so it doesn't slip under the radar. Anyhow, hope this was interesting. Don't underestimate the power of k-means. It's one of the most important topics in machine learning, and it's one of the most ubiquitous. So, having said that, make sure you fill out your what was it, the exit tickets, and I will see you guys Thursday.
So we're deciding like how to choose k. So from 3 to 4, like
There's less of a difference, yeah.
yeah.
So
So like, do you just visualize it? Or
no, use a silhouette score. I mean, maybe this was a bit misleading, but there's some methods I've seen in literature and documentation. Sometimes there's sort of what they call the elbow method, but if you scroll up, the silhouette score is objective measure of what the highest value. So what the highest value of your silhouette score is what you really want to do.
Okay.
So in other words, k equals 2 has the highest clustering value. K equals 3 has the second highest. K equals 4 has the third highest, and so forth. Yeah.
Okay, thank you.
The what? Oh yes, one thing I forgot to mention is I'm not going to be here Thursday, so Ed, who is an instructor for, also a data science instructor, will be filling in for me. I'll miss you guys all terribly, but anyhow, I'll be available for questions and online and whatever. Thursday, I'll be out of town. So yeah, Ed will be here, and you guys will talk about random forest and ensemble learning. Yeah, it is.
Question on stock. I was asking what the difference was between PCA and like F-classic.
Oh, they're very different.
Because it seems like both of them we select each feature.
Well, PCA is a transformation.
PCA is just an SVD, right?
No, it's eigenvector. So in implementation, it's SVD because SVD is more efficient to do.
It's just it's an eigenvector
It's an
decomposition.
it's an eigenvector decomposition,
Yeah.
exactly. But
And then you
F classic is definitely not. So PCA is a transformation to an alternate vector space.
Yeah.
So I'll adjust that.
Their
Yeah.
algebra, I get for the latter. So there were, these people they're really confusing because one we apply like
Thanks.
before we model, and then what it seems like when we apply after we model, right? Like we always do the modeling and then we apply F classic.
Yeah. So generally with F classic, we use it as part of the feature selection. But
For the Google search results and how you got
yeah.
so the scores.
Yeah, I'll definitely do that. Thanks.
Thank you.